All right, now that we've studied series and parallel circuits, it's time to combine the two into what are known as series and parallel combination circuits. Before we do that, however, it's helpful to review the rules for both series and parallel circuits, especially as it pertains to the potential difference rule and the current rule. The potential difference rule is essentially a statement of Kirchhoff's second law for circuits. It states that the gain in potential at the battery must equal all of the losses or potential drops out at the resistors in any closed loop. That will be really important in a moment. The current rule states that when you have resistors in series, all the currents through the resistors must be the same. In parallel, we also have a potential difference and current rule. The potential difference states that since all of the resistors are essentially connected across the terminals of the battery, that all the potential differences, the drops across the resistors, are exactly the same as the potential difference of the battery. The current rule, which is essentially a restatement of Kirchhoff's first law, says that when there are branches in a circuit, all of the individual currents must add to the total current. And of course, Ohm's law gets used all over the place in these types of problems. You just have to keep the subscripts together, V1 equals I1R1, V2 equals I2R2, and so on. And our rule for identical resistors in parallel, you take one of the resistors, values, and you divide by the number of resistors, and that gives you the equivalent resistance. All right, I would like to talk about the behavior of parallel circuits a bit, because now we're going to begin talking about what happens to the various measurements in a circuit when you start to change things. So I'd like to take a look at this circuit, and then we'll talk about what might happen if you add another resistor. So here we have a 6-volt battery, and we have 3 identical 6-ohm resistors in the parallel circuit. If we want to find the equivalent resistance, we can use our shortcut rule. Since we have 3 6-ohm resistors in parallel, you take the value of one of them, 6 ohms, and divide by the number of resistors, 3. That would give us an equivalent resistance of 2 ohms. But you can always use your 1 over equation to help solve that. Now, if we want to find the total current that leaves the battery, that would be the reading on that ammeter right there. Remember, ammeters are inserted in the circuit, whereas voltmeters are connected across items in a circuit. So the total current flowing in the circuit will be V total over the equivalent resistance, or 6 volts divided by 2 ohms. That would give us a total current flowing of 3 amps. So this reading right here would be 3 amps. Those 3 amps are heading out into the circuit. Now it turns out in parallel circuits, each branch of the circuit acts independently of the others. For example, this first branch is a 6-ohm resistor. It is connected to a 6-volt battery. Therefore, I1 will be V1 over R1. Since all the V's are the same, our V total is also V1. That's 6 volts over 6 ohms. That means we get 1 amp of current. So 1 amp of current takes the left turn and flows to the first resistor. In a like manner, 1 amp of current takes the second turn and goes to the second resistor, and 1 amp of current is left to go through the outside loop, which brings our total current up to 1, 2, 3 amps, which we knew anyway as our total current. Now, the question is, what will happen to the readings that are on the board, the 3 amp, the 1 amp, the 1 amp, and the 1 amp, if I add another resistor? We're going to add an R4, and it will also be an identical 6-ohm resistor. The choices are that 3 amps that's flowing from the battery will split up among the 4 branches, and each branch will now have less than 1 amp. The other choice is that 1 amp of current will also flow down the outside branch, because it appears each branch would like 1 amp. So which of the two is it? Well, it turns out, as previously stated, and I'll reveal, all branches in a parallel circuit are independent of each other. Not in a series circuit. All of those resistors are highly dependent upon their neighbors in a series circuit. But in a parallel circuit, when you add or remove a branch, it should not and does not affect the behavior, current, or potential difference of any of the other remaining branches. So, if we want to calculate the current in the outside branch, we could say I4 equals V4 over R4, which will also be 6 volts over 6 ohms, and we will see that we have 1 amp flowing out there, 1 amp, which raises a little problem, that these 4 now only add to 4 amps, and our current still says 3, but that's because that is not right anymore, because the resistance of the circuit has dropped, because in a parallel circuit, the more resistors you add, the lower the equivalent resistance. So the equivalent resistance just went down and more current will flow. How much current? 1, 2, 3, 4 amps. So the new current reading becomes 4 amps. So the take-home point is, in a parallel circuit, all branches are independent of each other. And if you add or remove a branch, it does not impact any of the other branches. However, the total current will be affected. You can think of this wiring connecting the circuit to the battery as being a little pipe that has to deliver whatever the circuit needs, and suddenly if the circuit demands more current, well, the total current wires then have to bring it. In addition to being able to work the numbers, it's also important for the AP exam that you be able to think qualitatively about potential difference drops and current branches. We'll tackle the potential difference drops first. As you know from Kirchhoff's second law, whatever potential you gain at the battery, you must lose out at the circuit. Here we have a 6 ohm and a 3 ohm resistor in series. And there are question marks on the voltmeters. You can clearly tell they're voltmeters by the way they're connected. We're going to need to figure out how much potential difference will get dropped at each of the two resistors. Will it be 3 volts and 3 volts because resistors like to share, or will it be more for one resistor than for the other? Well, it turns out, I'll do the reveal. In a series circuit, the potential difference gets dropped in direct proportion to the size of the resistors. That is, more potential difference will be lost at the larger resistor. The potential difference drops will be in the same ratio as the resistor ratio value. What that means is, if you're running an obstacle course, you need to save more of your energy, your potential difference, for the larger obstacles and save less of your energy for the smaller obstacles. Since these resistors are at a 2-to-1 ratio, that means the potential difference will get dropped in a 2-to-1 ratio. So since we have 6 total volts, what would fit in a 2-to-1 ratio? Well, that would be 4 volts and 2 volts. So you will get a 4-volt drop across the first resistor and a 2-volt drop across the second resistor. We also need to be able to think qualitatively about current branching. Here we have a parallel circuit with a 6-volt battery, a 6 ohm resistor, and a 3 ohm resistor. I guess before we talk branching, we ought to figure out how much current is going to flow, meaning what is the total current leaving the battery, because that is, after all, what needs to get divided up. If you use your 1/over rule, you will see that a 6 ohm and a 3 ohm resistor ends up having an equivalent resistance of 2 ohms. Remember that special rule where in parallel, the equivalent resistance will always be smaller than the smallest resistor. So if 2 ohms is the equivalent resistance, to find the current, we want to do I total is V total over the equivalent resistance, which will be 6 volts divided by 2 ohms. That means that 3 amps of current will leave the battery. So we'll denote that as 3 amps. That 3 amps leaves the battery, and now we have a branch. The question is, how much current will take the first branch, the 6 ohm resistor, and how much current will take the second branch, which is the 3 ohm resistor? You may have heard the expression, current takes the path of least resistance. It turns out that more of the current will go through the 3 ohm resistor than the 6 ohm resistor, but how much? How do we divide it up? I'll do the reveal. In a parallel circuit, it turns out that the current will branch in direct proportion to the size of the resistors. The current through the resistors will be the same ratio as the resistor ratio. However, more current will flow through the smaller resistor. So notice once again, our resistors are at a 2-to-1 ratio. That means that the current will branch in a 1-to-2 ratio. The same ratio, but more current will go through the smaller resistor. So a 2-to-1 ratio applied to 3 amps will leave us with 2 amp and 1 amp. So this meter must read 2 amps because the smaller resistor will get more current, and this meter must read 1 amp, which gets us to the 3 amp total current. Now, let's try taking a look at our first series parallel combination. Notice we have 2 resistors, 10 ohm resistors in series, and the end of the circuit has resistor 4 and resistor 3 in parallel, which makes it a series parallel combination. The goal is to solve for all the variables noted out on the right. We have a 50-volt battery connected to these identical 10 ohm resistors. Even though these resistors are in parallel out on the right, we can't say that their potential difference is 50 volts because they're not alone. They're not connected directly to the battery terminals like they would in a straight parallel circuit. So we have to think more locally in a series parallel combination. We have to slowly break the circuit down and try to find the equivalent resistance of the entire circuit. So you're going to look for areas that look series and parallel in small chunks. So notice R3 and R4 are in parallel with each other, and since they're both 10 ohm resistors, they can essentially be replaced with one giant 5 ohm resistor. If we were to redraw, it would be like having a 10 ohm and a 10 ohm and a 5 ohm resistor. Now you may note, now that we've taken care of the parallel part, that we have a series circuit now, a straight series circuit. And we have 3 resistors in series, and then we know that we add them together when they're in series, so the equivalent resistance of the whole circuit is going to be 25 ohms. Now, how does that help? The equivalent resistance is 25 ohms. That is what you need in order to find the total current. So I total, as always, will be V total over R total, which is called the equivalent resistance. That'll be 50 volts divided by 25 ohms, which tells us that 2 amps of current will flow in the circuit. So I'm going to put down that the total circuit current is 2 amps. Now, you may notice that the total circuit current has to flow through R1 and it has to flow through R2. It's useful when you look at a circuit to try to figure out which resistors will encounter the total current, and R1 and R2 definitely fit that bill. Picture water flowing in a pipe, and the water would go through both of those 2 resistors. So I'm going to take the 2 amps and I'm going to apply it to both resistor 1 and resistor 2. Now, how do we get the potential drops? Well, if I want to find the potential drop across resistor 1, we know I1 and we know R1, so we can do Ohm's law, V1 equals I1 R1. That would be 2 amps, because the total current is the same as I1. R1 is 10 ohms, so we get 20 volts. So I'm going to write down 20 volts for the potential difference loss across the first resistor. Notice the 2 amp also goes through resistor 2, which is also 10 ohms, so we're going to get a 20 volt drop here. If we think in terms of this reduced circuit, if you lose 20 volts here and 20 volts here, that only leaves 10 volts left for the 5 ohm equivalent resistor. Now I know there's really 2 10s there, but you can treat it as though it's that one collapsed 5 ohm resistor. This makes sense because you expect to drop less potential difference at the smaller resistors. So for V3, we can do I3R3, but we don't really need to do that. And plus, we don't really know what I3 is going to be yet, taking that branch. But what we do know is around any given closed loop, you have to lose all of the potential difference. So if we have 50 volts to start and we lose 20 and 20 at the two 10 ohm resistors, that gives us 10 left if we take this inside green loop. So I'm going to put 10 volts as the drop across the third resistor. And if I look at the outside loop, remember every loop behaves independently in a parallel circuit. So if we lose 20 and 20 and we take the outside loop, we must lose the same 10 volts out there. Now this is sometimes a bit confusing because it looks like this adds to 60 volts and the total is supposed to be 50. But what you really did is, if you did that, you'd be double counting V3 and V4, because it's really the same potential difference drop, because if you take the inside loop, you lose the 10 on R3, and if you take the outside loop, you lose the 10 on R4. So you can't double count them because each loop behaves independently. Now that we have V3 and V4, we can find these currents. I3 is going to be V3 over R3, and V3 we have just decided is 10 volts, and R3 is 10 ohms. So that means 1 amp of current will flow. And the numbers will be identical for I4. You will also get 1 amp because the numbers are exactly the same. This makes sense because the current, the total current, which is 2 amps, when it got to the branch, when it branches, those two have to add to 2 amps, the I3 and I4, and they do. So the take-home point when you're doing series and parallel combination circuits, you have to break down individual areas of the circuit that look like they're in series or parallel. And probably the best advice I could give is look for areas, look for resistors that you know will see the total current. If you can find the total current, that will then be the current through each of those resistors. That is probably the most important thing to know about series and parallel combinations.